Okay, we're live. Hi everyone. Yeah, so right now we have the Blackwell NVFP4 competition going on, and I'm sure as all of you guys know, most of the solutions or intended solutions are involving NVIDIA's new CuTe DSL / Cutlass 4. So we have Vicky here. Who has graciously, made these slides and is going to talk about CuTe DSL and provide kind of a nice introduction and also talk about a lot of the features and things you can implement in CuTe DSL, which should be helpful for the competition and also very generally for people who are interested in writing kernel code. So I will let Vicky take it away.
Thank you, Alex. And hello, everyone. I'm Vicky Wang from NVIDIA, and today I'm happy to give a brief introduction about CuTe DSL, and hope after my presentation it to help you to have a happy journey with your GPU mode competition. So before one more comment. So feel free to interrupt me if you have any questions about the content. So first, before let's look into details about CuTe DSL, let's have a quick look about the background. So why is the Cutlass? Because Cutlass is the background of the CuTe DSL. So there's a lot of the popular high-level generators and compilers in the world that allow users to write the kernels without knowing too many details about hardware. They are easier for user to quickly iterate on the new algorithm or features. However, they also had a lot of many details that hard for users to give the full control of the hardware features. So sometimes if you want extremely speed of light performance, it will be hard to figure out the magic optimization did by the high-level code generator or compiler. While on the contrary is the PTX, which gives all the control of our hardware features. However, PTX is too low-level abstractions that contains too many details that also hard for developers to do quickly programming. There we have the Cutlass. It gives expressive abstractions for developers to program on NVIDIA GPU and try to provide the simpler abstraction than PTX, but also give the full control to users. So let's have a quick look at the design architecture of the Cutlass. So the left diagram shows the multiple abstraction layers in Cutlass from the top to bottom. The top is the high-level interface that allow users to select some optimized kernels based on tuned configurations that users don't need to worry too many about hardware optimization details. While the bottom layer, which is the yellow and the gray box, are the CuTe abstractions. The gray is the atom abstractions that allow users to program on different Tensor Core and friends features on different architectures. And the yellow box is our CuTe programming model, which tries to provide some consistent programming model for user to program the kernels with excellent performance on different architecture generations. And the CuTe DSL actually is the Pythonic solution built based on these two layers and try to empower AI researchers and engineers to do quickly development prototype. We also give a GTC talk this year, so if you have interested about the more details, feel free to look at this talk. Okay, so how do we start to play with our Cutlass in Python? So this slide just show the quickly start up. Just pipe install this NVIDIA Cutlass DSL view and write your Python code. Run the Python hello world directly, then the U program will run directly on NVIDIA GPU. So in the rest of the slide, I will try to focus on the 4 program topics we provided to the GPU mode, and then use those 4 examples to help you run up the DSL features that may help you figure out how to write the code in CuTe DSL. Any questions before I go into details of the problem?
It doesn't seem like there are any in the chat right now. But I can just ask like a simple one, like generally what are the differences between CuTe DSL and say like Cutlass 3? And like what has been there before?
Okay, so the Cutlass 3 is mainly a C++ template-based library. So the developers can write kernels via Cutlass C++ framework. However, based on our observation, the C++ is good, but the template is so heavy and hard for developers to debug and build. Also, the C++ template using a lot of fancy features there. The compilation time usually is high. We measured and found that the kernel needed 10 to 20 seconds to compile. So sometimes it blocks the researcher to the fast iterate. And the industry try to pivot Python, like the PyTorch and Python. We think that Python will be easier for developers to phototype. And also when we write kernels in Python, there will be extremely less work for users to integrate their kernels into the Python framework. So we think that with better pivot to Python, thus we have the Cutlass 4, which try to build an entire Python ecosystem for Cutlass. But the first step is we release the bottom layer, which should be enough for users to try our features first and have fun with the full control of the hardware details.
I see. Is there any like major differences in flexibility between the two? So like, can you roughly do anything that you could do in Cutlass 3 in CuTe DSL, or are there some features that aren't available?
From feature side, I believe they have the same flexibility.
Okay, cool. I'll let you continue then.
Yeah. Thank you. So then let's look into the details. So the first example is Gemv. It's a quite simple examples where we will users to do the batch the Gemv computation, like the diagram showing the right bottom figure. The example the CuTe template just use very simple global load instruction to load data from global memory to register, and then simulate the computation with the FF main instructions, and in the end store the result back to the global. The example and the template is simple, but we would like to use it to highlight some very common features in CuTe DSL. The first are the two decorators in the CuTe DSL. The first is the CuTe. This decorator is mainly the entry point of our host side of the kernel to prepare parameters for the kernel, and including how we compute the grid size, block size, and the clusters you picked for your kernels. Because this is a kernel written in CuTe DSL, the kernel requires the CuTe tensor representations, and the CuTe tensor usually have some fancy layout. Not fancy layout, is the layout that our NVFP4 instructions, the Tensor Core instructions you will use, and hardware require some layouts that easily to make this Tensor Core to better fit and speed efficiency. So we would like people to starting from here to get familiar of those flow. And the second key decorator is the CuTe kernel. CuTe kernel is almost equal to the global entry point of our GPU kernel. And this table shows the color CoE combinations and requirement. So in short, the CuTe GIFT is not only the host side entry point, it also can be used to be inline function called by our CuTe kernel. So the third line in this table, but the kernel is the global entry point. We only be able to let the CuTe kernel decorator to call another CuTe kernel decorator. So these are the main difference. And the second point we would like people to get familiar with is the CuTe layout. CuTe layout actually mainly contains a bunch of the divide operations and slice operations. Those are typical CuTe operations. The partition and divide operations, which try to tiling the global tensor, like this diagram. We tiling this global tensor with M and K dimensions based on the MIMA tiler we gave there. This is the Gemv examples. I still use this terminology because all the rest program used Tensor Core. But for this one, even if it's a MMA Taylor variable naming, it's actually just for you to learn how to slice or partition your global tensor with some Taylor values. So we tailor this input a matrix with block M and block K you give for the configuration. Those are compile time variables. And after this tailor, we have this kind of hierarchical coordinate informations for this matrix. The block M and block N are the innermost chord here. And then the M contains multiple block M iterations, and the K dimension contains multiple iterations of the block K iterations. So we have this rest M and the rest K. Also, there is the rest L, which is the batches. But for this diagram, to keep it simple, I only have the batch equal to 1. And after we partition this global, we will slice this global tensor with the coordinates we want to. In this example, we have this block at X slice on the rest M dimension to move the CTA to the right block it wants to compute. And we use thread adding index to slice each row inside this block. So in the rest figures, it shows that once we slice this global tensor, from each thread point of view, it tries to locate it to one of these darker green rows from the A matrix, this yellow from this B matrix, and we'll then do accumulation to get the darker blue in the output matrix. So that's the mainly typical CuTe layout algebra in the program. So that's the second common feature we want to elaborate a little bit. The third feature I think is quite useful is the tensor and the tensor SIC concept in CuTe DSL. So tensor is mainly the composition of an iterator and the layout of the memory. So it contains support for global memory, shared memory, register memory, and the tensor memory. And the tensor SIC value is just a local data modeling for the CuTe tensor in value semantic and immutable. So when we do some global element-wise operations, we can load this tensor. This tensor we create here. After we slice, we already get a global tensor, and we based on this global tensor shape build a register tensor, and we can load the global tensor into a tensor SIC representation, which actually in the underlying is the vector operation. And then we can use a lot of vector inline operations to do tab conversion and element-wise operation. And after that, we store it back to the register tensor memory. And when we store it back to the register tensor memory, we can do read and write on this memory. So that's the tensor and the tensor SIC features. And the last common features we would like to show in the first example is the control flow. In CuTe DSL, we support the for, while, and if control flow, which allow user to write Pythonic control flows in the code. And our DSL compiler will do AST processing based on the condition given for this control flow to determine whether it's a Python evaluation code or is some AST rewrite generated the condition in the IR code. So there are different combinations. So in short, if the condition constant values, compile time static values, is just a Python evaluation of the code. But if it's the compile time defined conditions, it will go through AST rewrite and generate the SF node for the IR code. And the if, while, and for have the same requirement. But for the for, there is a special, which is the class range. Class range is almost equal to the Python range. The little difference is that the class range supports some advanced unrolling and pipeline control. If you are more interested, probably can look at our software pipeline examples. And here, just a quick elaborate about the class range fine grain control. In this code, the left side is a simple Gemm example. Here we do copy load A, copy load B, and once we load data from global memory to local memory, we do this Gemm to do the computation. And in this for loop, we have this prefetch stage annotation in the loop, and it almost equally to translate this simple code to a manually software pipeline scaling, where we split this loop to some prefetch TMA load operations. We load several data ahead of the computation. And then inside this computation, we can in parallel execute the computation with data prefetch in the previous stage, and then loading data for the later stages. So this is the power of the software pipeline. And with the Gemv algorithm, we almost show the common, very useful basic features for CuTe DSL. Any questions for this part?
It seems like people are still kind of shy in the chat. Oh yeah, by the way, I was going to say your camera was off a little bit. Oh, actually, no, there is one. Sorry, it just showed up. I'm not sure what example this is referring to, but they're asking why is NVFP4 converted to FP32 for compute? This might be the Tensor SSA example from the previous slide.
Yeah, it's just to show this Tensor SSA features, and it's just a simple examples at the very beginning. So when we share the CuTe DSL examples, we actually didn't use any Tensor Core or Blackwell advanced hardware features. Is just to help the participant to get familiar with our common DSL features and get familiar with the CuTe algebra and the layout expression. So we fully use the FMA, the IP32 data type to simulate the computation.
There's another question. You mentioned that the tensor the tensor object contains, I think they mean to say an iterator. Can you expand more on that?
Oh, I probably don't have examples here, but let me see the tensor. Okay, so here let's look at the left side code. You can see my mouse, the laser pen, right? This right. Okay, so here we have this GA variable. It equal to a global memory with some slice coordinate pointed to a tensor. So in this is a typical tensor operation, and instead this we have the iterator and the layout. So in some, if you really want to manipulate the tensor iterator, you can actually get the iterate from this tensor. It's just like the tensor concept used in Torch, where we have the iterator and the layout inside this tensor. And actually, you can extract the iterator, do some layout transform, and make tensor to get it back to a tensor you would like to use.
Yeah. I think also the CuTe/Cutlass docs has like a whole section about this. I can link it in the chat afterwards, but yeah.
Yeah, there is more details about the Tensor SI. This is the link. You probably can look into details of this documentation we have pushed in the GitHub.
All right, I think that should be it for now. If more pop up, I'll jump in, but I think you can continue.
Thank you. So let's look at our second example, which is the generic matrix multiplication algorithm. This one is a more interesting one, because for this one, if we want to achieve the speed of light computation performance on GPU, we need to use a lot of the advanced features on the Blackwell chips. So in this example, we actually focus to helping participants get familiar of our CuTe programming model. So in this example, the CuTe DSL template try to show how to leverage the TMA load to load different tensors, A tensor, B tensor, the scaling factor tensor of A and scaling factor tensor of B from global memory to the local memory, and then use Tensor Core. Also, because the hardware Tensor Core requirement, the scaling factor, A and B need to come from the tensor memory. So we have another S2T load operations to load them from the shared memory to tensor memory. And then we use the Tensor Core to do the computation. And after that, the computation result again stored in the tensor memory. We show people how to load data from the tensor memory to register and do a very simple store from the register back to a global tensor. So let's have some detailed look to show the CuTe programming models. So first is the TMA. For TMA, the code actually including the two parts. The first is the host state. We need to set up TMA atom and the TMA core tensor, because TMA, the hardware features require the code to show the coordinates for the tensor to the hardware to load. So at the host state, you will see we have the U2 function where the user needed to pick the atom instruction. In our examples, we use one CTA features. When you optimize this code to achieve the maximum memory efficiency, you may want to use the two CTA features. And then we gave it a global tensor with the layout we set in the host side to construct the tensor, and give the shared memory layout. The shared memory layout contains the Swizzling information. It tells the TMA when you move data from global memory to shared memory, you have to swizzle the data based on some shared memory requirement that later can be consumed by our Tensor Core. And also the tail size of this shared memory tensor and how many shared memory stages we have in the shared memory that allow the optimization to do prefetch. And then the Tensor Core instruction sizes. This is also used to tell the TMA. Later, we will see how it uses it to partition the global tensor to fit into the Tensor Core computation patterns. And this also carry the Tensor Core information that try to couple the data movement operation with the later computation operation. Once you set up the TMA and the TMA tensor in the host state, pass those two parameters to the kernel via CuTe decorator, then insert the device. The first is where we do this local tail. As we show in the Gemv, this local tail will use the MME to partition the global tensor into different block sizes. And then we have this TMA partition, which based on the TMA descriptor of the TMA atom we set up in the host side and the shared memory layout and the global tensor we also partitioned here to get the MM information, to get the shared memory, global memory layout for the TMA to do the copy. And in the end, for each K block iteration, we just call the CuTe copy. It will help us to copy data from global memory to shared memory to meet the all the hardware TMA requirement, and also prepare data in shared memory that later can be consumed by the Tensor Core instructions. So different tensors all follow the similar patterns to do the partition and loading data from global memory to shared memory.
There was a question in the chat. When you were describing making the TMA atom, you talked about swizzling from global to shared memory. Can you explain swizzling and how it relates to warps?
That's a good question. So I'm not sure if I can. I probably need to bring some swizzle data layout in here to help you understand. But in short, because we are trying to moving data from global memory to shared memory. In global memory, the data actually stored in either the column major sequence or the row major sequence, the M major sequence, OK major sequence. But when we move the data from the global memory to shared memory, we copy each of these small green box from global memory to shared memory. And when we do this kind of copy, to make it maximally use our memory bandwidth efficiency, we need to shuffle the data storage layout a little bit in shared memory to avoid something like the bank conflict. Because if we do this kind of streaming copy from this block to the shared memory, the first row and the second row, they will follow the similar pattern as global memory. However, for the computation, the Tensor Core, because it try to fetch data, let me change wait a moment, let me change the because this is the granularity of our global copy set. It sometimes not equal to the instruction set, but the Tensor Core probably will do more smaller granularity consuming the data. So it probably at a time only consume part of this chunk of the data from the shared memory. So this set probably not meet the best memory elementary requirement we have in the local memory. For example, for the shared memory, we want the 128 accessing for different bank and allow the data have no bank conflict in each thread. So we probably will try to change this chunk of data, do some swizzle, and when we copy it into shared memory, we probably want to make this match some shared memory requirement to meet the elementary requirement of swizzle patterns that avoid the bank conflict. So that's the simple idea. But I can share find some swizzle details in the public documentation to you later, then probably help you get a better understanding.
Amazing, thank you.
Okay, so if there's no part on this side, let's continue to go to the S2T copy. As I just mentioned, the scaling factor A and the scaling factor B, after we copy them from global memory to shared memory, the Tensor Core requires them to be stored in the, from the global memory to shared memory. The Tensor Core requires those two tensors to be stored in the tensor memory instead of the shared memory. So we have this S2T copy code in the example to show how you copy data from the shared memory to the tensor memory. Again, first we need to pick the right S2T copy atom. I think the instruction details could be found in our CuDA programming guide to show the different configurations of different S2T copy instructions. And then we have this tilde copy operation to make a tilde copy atom, object. And once we have all of them, we do this partition source to partition the shared memory. And we have this partition D to partition the destination tensor memory. And again, we do this copy to copy data from shared memory to the tensor memory. And after this partition, actually the data in the shared memory and the tensor memory follow some CuTe layout convention, where we have the atom set, which set in each instructions the copy granularity of this instruction, and how we move around the m dimension or n dimension or the k dimensions to copy each of the smaller granularity data from the shared memory to the tensor memory. So here, when we do this slice, we actually try to copy the entire data from each k block to the tensor memory. So in general, again, the pattern is kind of that picking the right atom, get a tilde copy object, and use this tilde copy to the partition S and partition D and do the copy. It's similar to the TMA partition. It's just a TMA partition is a syntax, not syntax. It's a simpler abstractions that combine the partition S, which is the global tensor, and partition D, which is a shared memory tensor, to return two operations here. Okay, I will continue. And then, And then we come to this Tensor Core. In the Tensor Core side again, we pick these Tensor Core instructions this is the tensor instruction level shape. And also we use one CT configuration, and also we tell the Tensor Core operands coming from the shared memory, where says the A tensor and the B tensor coming from the shared memory. And after we configure the child MME, we use this to construct the descriptor from the shared memory tensor, which is the operand tab that can be consumed by the Gemm operations. And we convert the shared memory A, shared memory B, and the tensor memory to the descriptor tab and tensor memory tab we needed for this Gemm operations. And once we configure all the operand tab, we do these loops on each of these K block iterations. We just show that the K block is 256, but for the instruction, needs to do a small amount of the data every time. So we here set the scaling factor iterators. This is where we have the tensor concept later, means that the tensor is iterator composed with layout. So here we set iterator into the child MME and then call the CuTe Gemm to do this Gemm computation.
So you mentioned at the top, like you need to pick the right tensor core operation for like the tiled MMA. What, I guess, like does this imply that there are several different tensor core operations that could be used and some are better than others?
Yeah. The hardware actually provides different sizes of tensor core that allow user to pick, because for example, if the problem set like Gemv only have n equal to 1.
I see.
So if you use a very wider tensor core, actually we are wasting a lot of computation power.
Right. Makes sense.
That's why we need to pick different sizes to balance the computation resource and the memory loading.
I see. Thank you.
No problem. Okay, then let's continue. After we finish the computation, the data already in the accumulation result. So in the epilogue, we have to do this tensor memory to register copy to get the data back to register. So again, the sequence will be construct the right tiled tensor memory to register copy instructions. And after that, you may notice there's a little slight differences about this get slice. We put the thread ID instead here, because the T2R copy is the same T instructions. So we have the different thread ID into it to move thread to the right granularity of the computation result to different position. And then again, we do this kind of partition source, where is our tensor memory, and we partition the destination, which is global memory. And we use this partition global memory shape to construct a register tensor memory here. And then the last step is we copy the tensor memory to register to get the data prepared for the final simple global memory store operations. Because the code is just a demo, in the template, I directly copy the data from register to global memory. So here, after this step, the RMM will follow the similar global memory partition layout to construct and do the copy. And the global store operations will be very simple to directly copy the data from this RMM to the global memory. That will be quite simple. If you want to do more optimization to change the layout, you probably will change how you construct the register memory here and do some Swizzling shuffle to store the registers to the shared memory and then use shared memory to the global memory. But all in all, if we look at all the copy sequence, it all follow the similar program model that we picking the right atom to the partition source, partition destination, and then to the copy. So here is a summary of our CuTe programming model, which is very typical, and you will get familiar with this program model in all our competition CuTe template example. That is for copy. Especially for the global tensor, we have this local tile to telling the tensor, global tensor. And then for all the global tensor or the local tensor, we have this partition source and destination, or use this TMA partition to simplify your TMA code logic, and then do this CuTe copy to iterate on your partitioned tensors. And for the Tensor Core computation, we just make fragment on the local memory we prepare there to make it meet the instruction required operation type, and then call the CuTe Gemm. So the sequence and the logic will be quite similar. The difference is that how you tune and tweak the atom selection and the Swizzling patterns to ensure you have the maximal memory bandwidth utilization and the best Tensor Core efficiency utilization. So that's the optimization questions, leaving for the participant to explore and try on your side.
Yeah, do you think you can provide a little bit of intuition for how somebody would go about optimizing this stuff for the competition? So like basically it seems like from the examples that you've provided, like there's a lot of flexibility in like what instructions you can use, like what tile sizes you should choose, and things like this. And they all will give you like functionally correct kernels. But sort of like for someone who's competing for the first time, like what can they do to sort of make things faster? Or like how would they change their code beyond like the template, for example, to make their code faster?
Probably I can, let me see, I can. Okay. Let me see. From the CuTe DSL template, I'll probably only be able to find a piece of code that allows you to see how to use this. But let me share this link to you. Maybe we can share to others via the chat. Wait a moment. So actually in our GitHub lab, we have a tutorial examples. That examples currently show the optimization tricks we can play with the Gemm, but that tutorial is focused on the half precision gems. So in there, actually, there are a lot of things we can do. So the first, as we just described, is the atom size, because different atom depends on your problem size, how many memory you are going to waste, and how many computation you are going to waste. That may be the configuration many people can be explored. The other thing is, let's see if I go back to the Gemv examples, you may notice this software pipeline optimization. Because all our computation CuTe template, I just do a simple for loop where I do load, and then do the computation. So in every K block iteration, the computation have to wait the data to be ready in the local memory first, and then do the operation. However, there is a software pipeline examples. In ideal case, we actually should parallel the data copy operations to this mass operation, the mass operation. So the ideal case is that we prefetch some of the memory operations ahead, and when we do the computation, the data should already be ready in the local memory. And in parallel, we prefer data to the other buffers. So that's the other optimization we usually do. However, this is a typical software pipeline optimization. But both TMA instructions and the Tensor Core instructions, they are asynchronization instructions. So actually, the typical Blackwell program model is warp specialization. So let me back to my slide here. So sorry. After this part, we get familiar with the operation sequence. Let's jump to this pipeline slide first. We actually have a bunch of slide operations which try to do this producer-consumer control between the copy and load instructions. So instead of software pipeline, we can also have the warp specialization optimization to let different warp to do different copy and computation instructions. Then, because they are asynchronization instructions, each word won't be blocked by the other side. So they can have better concurrency on GPU to balance the workload. So that's the pipeline part. But also those pipeline will guarantee the memory orders and the operation correctness. So that's the part user needed to explore. So my also based on the tutorial, if people look at the tutorial, I think those are the major operations and the optimization configurations user can try, and it will give you already some excellent performance. The rest probably will be some fine granularity optimization, because in all our examples, I'm trying to do the epilogue storage on a block granularity.
I see.
So it means that for each block, I directly copy a accumulator from the TMA to the register and then store the register to the global memory. In fact, if we want to have this optimize the epilogue, we probably want to also do some tiling on the epilogue part. Then we can do the T2R copying and the global copying concurrently. Some kind of the optimization trick we use in the software pipeline. So let's summarize the software pipelining, the reg atom configuration, which could be the key optimization user should try when they want to get higher perf on those problem sizes.
Gotcha. Thank you.
No problem. Okay, so now we almost get familiar with this CuTe programming model and get familiar with this pipeline optimization. And let's look at another DSL feature is CuTe Struct. We have this Struct data that allow users to manage shared memory and to ensure the data match some element requirement in the shared memory set. So usually we use this to allocate this mem barrier, because those barrier will be used for the pipeline to do the producer-consumer data synchronization. So we use this to group bunch of our barrier operations into this structure to ensure they match some element, and later that will be easier for us to do the shared memory efficient access for this barrier. And also we have this shared memory allocator utils. It will allow users to use this allocator operations to allocate shared memory for a buffer with static shared memory layout. So those are used for structured data and utils for users to manage the shared memory buffers. Okay, we already look at this pipeline slide, so I will going to skip. Okay, after here we finish the Gemm example introduction. Any more questions? No, I'm going to go to the next example.
There was a question, which is, do you have any recommendations on how to change how you slice memory based on unconventional or small matrix sizes?
This is a good question, but I think because when you said this is unconventional or small matrix sizes, it depends on how small you have there. And if it's really very tiny or small, I think it's probably not the mass computation cases. So it's probably will fall back to the memory bound cases, which means that how we maximum use the memory bandwidth will be the key importance. So at that moment, I think you probably can ignore a little bit of the Tensor Core set let's think about how the memory operations, what's the best configurations for you to load them from each memory to the other local memory, and how you do some kind of software pipelining. Because even if we do memory copy, we are probably still going to do global memory to local memory and do some kind of the local memory swizzling between, and then copy to another memory space. So the short is that try some software pipelining to make sure your memory operations also in some kind of concurrency to have the latency to get you better most memory movement efficiency. So that's the typical optimization suggestion.
I see. And there's another question: what kinds of things in NCU or Nsight Compute would be useful to look at when trying to optimize a warp specialized kernel and understand any bottlenecks?
Usually, I probably will start from the speed of lag section, because that speed of lag section will first tell me whether the kernel bound down the memory efficiency or bound down the computation efficiency. And then I probably will check the memory sections to see, okay, if my kernel bound down the memory is bound down some local memory instead of the DRAM efficiency, I probably want to check the local memory traffic footprint to see if I'm doing too many redundant load from global memory to local memory. And actually, this bring me another optimization I probably just forgot to let you know is about the cluster optimization. Because the cluster optimization is another hardware features that allow the users to load data from the global memory to the local memory and do some broadcast to further reduce the pressure on local memory. So the memory section will give you all the breakdown details about how you memory traffic size from global to local, and how you memory traffic size from the local among different local space. So based on those analysis, you probably get a better sense about where the memory stacks there, and you can continue focus on the memory part. And then if you kernel already bound down the mass part, you probably can check the instruction static sections to understand which instruction is the long core on your computation part, and then continue to do so far forth analysis there to figure out the details.
Got it. Thank you.
No problem. Okay, let's continue. Then this is the dual Gemm. The dual Gemm is where we have this A matrix and a 2B matrix, and the 2B matrix have the same n dimension. And we do this computation to get the two accumulation result. And before we write this accumulation result to the global memory tensor C, we do sweep value on one of the computation result, and then do an element-wise operations to do the global tensor. So if we look at CuTe DSL features, for these examples, because it's quite similar to Gemm, the difference is that you have to manage another actual bit tensors there. So you will see a bunch of the actual Taylor partition in my examples. So the key optimization features we would like this algorithm for you to see is that one is that we have this epilogue operation lambda expressions in our code. So the kernel functions, kernel signatures have both the compile time argument and the dynamic argument. The dynamic argument is the kernel parameter, and the static argument actually is some inline functions that can be applied to the kernel to get better efficiency. So here we have this lambda functions to illustrate how we want to do the sweep gallo operations. And here again, you see the power of the tensor SSA operations, where we load the RMAP tensor to the vectorized operation, apply the CLU operations here directly. That will be very simple. You don't need to manage elements one by one. And then we do this element-wise multiplication between the two tensor SSA operations. So all this will simplify your implementation, and the tensor SSA features will help you handle each element-wise operations. So that's the features we want to people to explore and to try in this epilogue fusion use cases. And okay, so about Swift and a quick question, because it's quite similar to Gemm, and these have more computation. So I think for this example, you probably need to focus on how to use Tensor Core to get the best computation efficiency. Okay, then let's look at this group Gemm. I think this is the most complicated examples you are going to explore. So first, elaborate about what is group Gemm. Group Gemm have multiple group of matrix multiplication, and in each group, the M and K sizes will be different. So the code needed to compute the data each CTA needed to process on the fly. So the tricky part is that we need to have TMA update operations in the code. So unlike Gemm and other examples, at the very beginning of the code, the logic is that we need each CTA to figure out where the data is needed to load, and which tail is trying to compute and store the result to the right global tensor. So after each city, based on this coordinate and the problem size, to figure out the right group and the right coordinate is going to do, the rest things that we need to do online TMA descriptor update inside the kernel. So the most of the tricky and the fancy part in this group Gemm is we have a TMA map manager utils for you to do this kind of the tensor map update on the fly. So the template is quite simple. I use some very experimental program model that I let each CTA do one output tail of the problem size. So I give each CT a global tensor map pointer where to show is A tensor, B tensor, scaling factor A tensor, and scaling factor B tensor at the beginning of the code. Once I figure out which group, I let the grid dimension Z to show the group index. When I figure out my CT compute to which group, I let it point to its global tensor. And then I use this TMA descriptor I created at the host side to construct the new TM descriptor in shared memory. And I fill this shared memory tensor descriptor with the static tail size and static box sizes, but with fake global address, global dimension, and global thread information for this shared memory TM descriptor construction. And after this, because I have my real tensor A, scaling B constructed online with my device operations, I update the descriptor information with this real tensor information and store it back to the global tensor map pointers I get it at the beginning. And after finish this, I need to ensure all the TMAM tensor map update done in the global memory. Then after this, we finish all the TMA update inside the kernel. And the rest part will be very similar to the other Gemm and dual Gemm operations. We do the TMA operation load and the scaling load to do the Tensor Core to do the operation. So all those TMA partition and all those TMA update and the management will be the key tricky part for this group Gemm, and it will be very complicated sometimes for user to figure out. Any questions on this group Gemm?
Yes, sorry. So actually, I guess there was a question for the dual Gemm. They were asking, how should I stage data through shared memory for dual Gemm? Should the output of the first Gemm stay in shared memory for the second Gemm's input, or is it better to spill the registers and avoid shared memory pressure?
Oh, let me see. So first, I think this purple and this purple output, they are in the tensor memory. So in the tensor memory, the second part is that okay, I needed to do the element-wise operation. So those must be in the registers. I think you probably can have a try because on Blackwell, all those memory operations and the Tensor Core before the epilogue all in the local memory. There's less register usage before the epilogue. So you can explore to load the entire data into register, but if you pick a very large MMA count, your register probably will be spilling. So remember, I mentioned that you want to do some subtiling on the epilogue. So you can every time pick a subtiling of the epilogue, load it into register, do your element-wise operation, and then store into shared memory to do the rest of work. And then you can do this kind of the element-wise operation, register and share memory movement in concurrency at different stages to get the best efficiency. You probably don't want to store the data into share memory directly because your share memory will be used to prefetch the A tensor, B tensor, and if the epilogue consumes too many of the share memory, you probably will reduce the stage for your main loop to load the data to not hungry the tensor core. So I think my suggestion is that try to slice in the epilogue to do count of the register and the share memory staging and in concurrency to get to the best efficiency.
Perfect. I think that should be it in chat. I think you can move on.
Okay. So I think I've also done my group Gemm introduction. So again, the fancy part and the complicated part for the group Gemm is the tensor descriptor management. Once you figure through the tensor map update, I think if we look at each city's from each city's point of view, the rest part will be very similar to the Gemm and dual Gemm. So I believe if you get good performance result with your Gemm and dual Gemm optimization, you can apply the similar optimization to the group Gemm after you figure out the right TMA descriptor update logic. Okay, then I would like to introduce some other interesting features for the CuTe DSL. One is the compile and the run. In our template, you may notice that I have some kind of the customized compilation key used in the example. Because we are DSL, we have the Python. So sometimes the compilation time is quite long. So when we benchmark the kernel, we probably don't want to recompile the kernel every time. So here we have this cache key. For this cache key, we can allow user to customize the key you want to use to index if you kernel already in this global cache key, you change some static compile time configuration that you need to recompile. So for this compile kernel logic in the group Gemm, I use problem size as the key because different problem size have different group numbers. So it will change how the kernel signatures to launch the GPU kernel. So I use this as my customer key, and I have a bunch of the parameter preparation in the compilation time to use fake tensor. So I have this make pointer operation with take a non-pointer to ensure I compile the kernel with the right signature, but it doesn't contain the runtime information. And once I compile the kernel and cache it in the key, when I actually launch my kernel, I first check if this configuration already cached in the key. If it is, the compilation time will be simplified. So here, after I get this compiled kernel from my key, I actually update the parameters with the real runtime informations and then launch my kernel. So these are typical the customized cache strategy we provided in CuTe DSL, and there is the link about the details of this cache. If you have interest, you can have a more look on the details. And this part will be quite useful because when you write CuTe DSL kernel, you probably will hit some issues I want to debug a little bit. I usually find the print is quite useful for me to figure out if my layout is wrong or if I copy the wrong data to my memory. So we have the pattern print. So this print allows us to print all the static informations, and we have the CuTe print. This can be used in both the host side and the GPU side. So CuTe print will print the value of the runtime parameters. And we also have this CuTe print tensor utils that will dump the content of the tensor. But please pay attention, the CuTe print tensor only support limited data type. So if you really want to check your narrow precision data, whether they're right in the local memory, when you load you probably need to rely on Tensor SSH to load your narrow precision data to the vectorized operation. Oh, sorry, not the Tensor SSH expression, and do the convention to convert your narrow precision to float 32, and then to do the print to check if the value match your expectation. That's also why we use the FMA as a Gemm way to help you run up on this part. That probably will help you to get some debug hint later in your code. So this just the rest set just show different print. So the first two are the pattern print. So you will notice there are a bunch of the question mark because the pattern print only print the static information. So for all the runtime information, it won't print details. So you will see the question mark in the print result. And the CuTe print will print all the information. So you will see all the runtime variable for the question mark, which will help you check if your partition result gives you the expected result on the ResGem, or so forth, so forth. And then we can check the global tensor and the local memory tensor content. So here, we check the global tensor, and it print all the random value we set in the tensor preparation stage. And after we partition the global tensor to the partition result, we can slice the tensor to print a part of the result, which is only 108 partitioned block M data to the screen to check if you slice the right data you want from the global tensor. And also you can add this verbose annotate. It will give you all the details. It will print all the 128 element. I didn't show all of them to simplify the example. I think this quite be used quite helpful when you try to debug some function issues in your code. Okay, then here we go. We have this inside debugging tool. So before we go into this inside debugging, there's another several configurations you can use. The first is the keep IR. If you want to look at IR, you are familiar with MLIR, you can dump the IR to check if some IR bug is obvious to you, and you can quickly identify the problems. You can also keep the PTX or CuBin to use our NVIDIA CUDA toolkit to do some examination to see if there are some racial spelling or some bad SAS you feel not good. But that probably require you have some good understanding about the PTX and SAS. Also, we have this line info features. If you pass this annotation to our compile function, actually we will have this kind of the source and SAS correlations showing inside. Please ensure your inside report stays in the same folder with your source code. Then it can show these details. And when you click the instruction, for example, here is my T2 share memory copy. It will point to my source code to show here I do the code. So if you are familiar with Insight and try to do some instruction level optimization, you probably notice there may be some SAS generated looks not good. And then you can click to see if the SAS generated from some, for example, some cases you forgot to do loop paralleling, and then it generates some unexpected loop conditions for your code. So this will also be quite helpful. Also, again, this is some features we are still enhanced and polishing. So maybe you may notice some mismatch between the source and the source. That's something we are continue to improving, and you probably can report issues in our GitHub, and in the later we may continue to enhance and make it better. The last feature I want to introduce is this Inline PTX feature, because the CuTe DSL is the pattern front end. In the backend of CuTe DSL, there are a bunch of ML framework we are built that is something user invisible. So it's possible that when you try to do some fancy low-level granularity optimization, you may notice some features that are not supported in our view. In that cases, we actually support this inline PTX. If you are familiar with PTX syntax, you probably can try this feature to work some view issues that features are not supported in the view. So that can be another useful features to help you unblock your optimization work.
Yeah, there was a question actually in the chat, which is basically like, do you think it's possible to hit, I guess, close to speed of light using only CuTe DSL, or will generally like top solutions for these problems use CUDA or PTX?
I think CuTe DSL can help you reach the speed of light performance, because we already released a lot of such kind of examples where CuTe DSL. But because our review is continuing in developing stages, and there are a lot of hardware features probably in the release version is not ready yet. Gotcha. So in that case, you're probably, because this is competition, this depends on whether the GPU mode will continue update view to the updated version. So for that cases, maybe some corner cases, the view used in the GPU mode is not contain the feature. So you have to use some of these tricks to manage the optimization.
I see. There was another question for the debugging slide, and they're asking, does CuTe.printf require register memory space? They're saying they weren't able to get it working when reallocating registers with set max and reg.
No, because if you look at my, they are all global memory. But it depends on what you are trying to do print there, because there indeed some we indeed have an enhancement of our CuTe print, because I believe in some older version our CuTe print probably only be able to print tensor in complicated composition CuTe layout or Swizzled CuTe layout. You probably need a slice to ensure you print a linearized buffer, and then it probably will give you the right result. We enhanced this in our latest view, but again, that depends on whether we are going to update our view in this competition. Yeah.
Yeah, sorry, you can go on from here.
Yeah, I think that's almost all the features and the details I want to introduce in this talk. And there are some other useful resources you probably want to have a look. One is Chris, which is the founder of CuTe, already gave an introduction of CuTe in our GPU mode competition. I think this contains all the details of CuTe algebra and the layout transform. So if you really would like to understand more details of how this CuTe do the magic and fancy layout operations for you, probably look at his presentation. And also we have a bunch of CuTe DSL documentations that have detailed elaboration of most of the features I have in this slide. And then we have a lot of DSL examples. I believe most of the examples already show how to achieve the speed of light performance. But those examples contains too many optimization details, so it may be hard for you to look at the first glance. So that's why the CuTe DSL template I provided for this example just show the simple logic of the function and the algorithm. And you probably can use those templates to understand the common features, and then check our examples public in the GitHub to try to apply the optimizations used in our public examples to your competition and try to gain the speed of light performance result. hope after this presentation you have a better journey and experience with our CuTe DSL.
Yeah, perfect. Thank you so much. Yeah, I guess maybe I'll leave a few extra minutes if any more questions roll in. I sent a message in the chat, but if it wasn't clear, like the other kernels that Vicky went over are going to be in the competition. So if you have any more questions, like I recommend asking now because this is, I guess, the perfect time to ask. But yeah, I guess otherwise, like, good luck everyone on the competition. I think there were a lot of very, very cool solutions to the Gemv kernel. The Gemm kernel is ongoing. I think there's probably 2 weeks left on that, maybe even more. But yeah, if you guys have any questions, please ask. Otherwise, thank you so much. Oh, there's one. They're asking, is it possible to have runtime asserts in CuTe DSL?
Yes. If you check the compile time static features, yes, you can have the runtime assert in the code.
Another person is asking, will we have access to the slides after this talk?
Yeah, I will send this lecture to the poster.
Yeah, we'll put it on the lectures repo. Another person asks, I think they're referring to Qtile, like the new thing that came out. What is the difference between that and CuTe DSL?
So I think CuTe DSL is more low-level pattern primitives that you have as we mentioned in the first slide, you have the full control of all our hardware features. But the Qtile, as far as I can tell, I think is more high-level pattern solution. So if you look at Qtile examples, I think it won't have too many hardware details, and the Qtile backend will help you to all those fancy and optimization in the backend compiler. So I think it's a high-level pattern solution that will make you pattern prototype exploration be much more easier because CuTe still contain too many low-level details. Some users already feedback us that is hard to learn and also hard for people to write at speed of that kernels. But Qtile will be much simpler for you to use at the API level.
Yeah. Any tips for debugging pipelines and ordering of operations?
Actually, depends. So I think you can try several things. One is our not inside, the computer standing tether tool. There are some tools that you can run to check if there is some risk contention or memory illegal operations in the code. The rest thing I think is just to try different print and comment on the code and relate to the pipeline to see if you can root cause the harm. And the last case is the last situation that you can also try CuDA GDB if you're familiar with how the GDB works there. You can break and run the code and stop on the problem you hit in the code and try to check which thread or which work actually bring the trouble for you, then try to deduce where the source bring the trouble for you.
Perfect. Thank you so much, and good luck everyone in the competition.
Yeah, good luck to everyone. Hope you have